Okay, welcome back to McNabb Chemistry, and today we're going to have a look at the second form of stereoisomerism known as optical isomerism. Okay, just to start with then, just a reminder then that stereoisomers are compounds which have the same structural formulae but the bonds are arranged differently in space. Okay, so optical isomers then are compounds that rotate plane polarized light due to the presence of a carbon in the molecule that has 4 different groups around it. Okay, optical isomers therefore have no center of symmetry, plane of symmetry, or axis of symmetry. Okay, so if you're looking for an optically active compound, basically you look through the molecule, you look at all the different carbons, and you look to find a carbon that has 4 different groups around it. Okay, right, so what we're going to do now is we're going to consider a molecule that forms optically active isomers or optical isomers. Okay, it's this compound here, 2-hydroxypropane nitrile, so meth, eth, prop, so it's propane nitrile, and then I've got an OH group on the second carbon, so it's 2-hydroxypropane nitrile. And as you can see in this molecule, this carbon here, it has an OH group there, it has a CN group there, has an H group there, and it has a CH3 group here. So that carbon there has 4 different groups around it, and we say that that carbon is chiral, okay, and that would form optically active isomers. Okay, so we say a carbon with 4 different groups around it is chiral. Okay, so optical isomers then, they rotate plane polarized light, okay, light that's made up of waves vibrating in one plane only in opposite directions. Okay, so one of your enantiomers, one of your optically active isomers, would rotate plane polarized light clockwise, and the other one would rotate plane polarized light anti-clockwise. Okay, so let's just check through this again, so make sure we understand what's going on. Optical isomers rotate plane polarized light made up of waves vibrating in one plane only in opposite directions. Okay, one will rotate the plane polarized light clockwise, sometimes shown as a plus or dextro-rotatory. Okay, and the other one will rotate it counterclockwise, which is known as minus or lauvo-rotatory. So one will rotate plane polarized light to the right, dextro-rotatory, and one will rotate plane polarized light to the left, which is lauvo-rotatory. Okay, so let's look at this, the 2-hydroxypropane nitrile in a little bit more detail. Okay, this is a mirror here. Okay, so there's my carbon, so this is my 2-hydroxypropane nitrile. Okay, that's my carbon, that's my chiral carbon that's got 1, 2, 3, 4 different groups around it. Okay, the enantiomer of that, the optically active isomer of that, is a mirror image of that. So I put a mirror there and I draw an exact mirror image of that, and this is absolutely key in the exams. The distance between that end and that end to the mirror and the mirror to that end should be the same. It's almost the same in my diagram here. That's possibly a little bit too short, but it needs to be exactly the same. Okay, and then look how I've drawn the groups here. So OH on that side, HO on that side, HH, CH3, H3C. Okay, so they should be mirror images of each other, and this is the key. You know that you've got an optically active compound when, firstly, as I've already said, you've got a carbon with 4 different groups around it, but also, this is key, the mirror image is non-superimposable on the other enantiomer. So if I was to pick that up off the page, I wouldn't be able to put it down on top of that structure there. So if I pick that straight up off the page, I can't superimpose it onto there. Okay, so it's a non-superimposable mirror image. Okay, so note up here, optical isomer 1 and optical isomer 2 are non-superimposable mirror images. Okay, so optical isomers of the same molecule are known as enantiomers. Okay, so these 2 optical isomers, we have a special name for them. They are known as enantiomers. Okay, and let's have a little think about this then. So let's say this enantiomer rotated plane polarized light to the right. this one rotated it to the left. Okay, what would happen if we had 50% of this enantiomer in a mixture and 50% of that enantiomer in a mixture? Well, surely if that one's trying to rotate it to the right and that one's trying to rotate it to the left by exactly the same amount, then they will cancel each other out, and that's exactly what happens when you have 50% of both enantiomers. Then the plane polarized light is not rotated. So when we've got 50% of both enantiomers in a mixture, the plane polarized light is not rotated. Okay, so here we go. So mixtures of enantiomers. So if we've got 50% of the D version and 50% of the L enantiomer, one enantiomer is trying to rotate plane polarized light to the right, the other to the left. Therefore, the overall effect, if we have a 50% mixture of both enantiomers, is that plane polarized light is not rotated. Okay, and when plane polarized light is not rotated by this type of mixture, we say that we've got a racemic mixture, and the two enantiomers are known as racemates. Okay, so when we've got a 50% mixture of the D and the L enantiomers, we have a racemic mixture. Okay, and the two enantiomers are known as racemates. Okay, so that's optical isomerism. However, let's just have a little look at plane polarized light to make sure we fully understand what plane polarized light is. Okay, so we'll all know that light is a transverse wave. Okay, so here's my light here. Lots of transverse waves, all going in different planes. Okay, so that one's going up and down, that one's coming out to the side and then back through, that's coming out this side and back through, this one's going down towards the bottom. Okay, so we have lots of transverse waves in our light beam here, but we have them all in lots of different planes. Okay, so what we need to do is we need to create to find out whether a compound is optically active and create some plane polarized light. What we have to do is we have to separate out all these different transverse waves in different planes. Okay, so that we end up with plane polarized light, which is this wave here, which is just basically a transverse wave vibrating in one plane only. Okay, so that's what plane polarized light is. So it's just where you've got a single transverse wave vibrating in one plane. Okay, so that part is plane polarized. There we go. Right, final little summary then. Make sure we understand what all the key words mean. Right, so optically active compounds, a recap with emphasis on the language. So let's take our 2-hydroxypropane nitrile. That's my 2-hydroxypropane nitrile. That's my other enantiomer of my 2-hydroxypropane nitrile. These are both non-superimposable mirror images. That's my mirror. Okay, so we understand what a non-superimposable mirror image is. I take that molecule, I pick it up straight off the page. I can't superimpose, I can't put it down onto that enantiomer there. Okay, an enantiomer, that's just one, or enantiomers are your optical isomers. Okay, dextrorotatory means that one of the enantiomers will rotate plane polarized light clockwise or to the right. Bauer-rotatory, plane polarized light rotate to the left or anti-clockwise. A racemic mixture is where you've got 50% of both enantiomers. Okay, and remember, when we've got 50% of my D and L forms of my enantiomer, then we have a racemic mixture which doesn't rotate plane polarized light. When we have a 50% mixture of the D and the L enantiomer, these enantiomers are known as racemates. Okay, chiral molecules are molecules that have a carbon with 1, 2, 3, 4 different groups around it, and you'll often see a chiral molecule indicated on your molecule with a star here, like this. Okay, to show that that carbon is chiral. Okay, an asymmetric carbon atom, well, that's an asymmetric carbon atom. An asymmetric carbon atom is a carbon atom with 4 different groups around it. Okay, thank you for watching. I hope that's been helpful, and don't forget to like and subscribe and click on the bell notification to stay fully updated.